inductors. That is the topic of discussion for today. So inductor is a coil with any number of turns. If we consider the voltage across the inductor as VL, the current flowing through the inductor as IL, then the value of the inductance of this coil is L, and the units of this inductance is Henry. So the relationship between voltage and current for an inductor is voltage VL equals to L, and the derivative of current I. That's the equation for an inductor, which relates the voltage and the current. So our discussion about inductors' behavior will be around this equation. So with this equation, if IL is constant, no change with respect to time, that leads to DIL over dt equals to 0. That leads to VL equals to 0. So first, a concluding statement about the behavior of the inductor is voltage across an inductor is 0 when current flowing through the inductor is constant. So what this voltage 0 means, this voltage 0 tells us that this is a short circuit. So an inductor, when it's fully charged, acts as a short for DC. Okay. So for this inductor, let's say here is a graph between the graph for the current for the inductor, so IL as a function of time t. Now what is happening if you look at the equation V equals to DIL over dt, here we're looking at the change in current with respect to change in time for this instant. So here the change in current is 4 minus 2 as 2 amperes, and the change in time is 0 seconds because it's the same instant it's happening. So this leads to infinity, which is impossible. So that means for an inductor, current cannot change instantaneously. Second concluding statement. For an inductor, current cannot change instantaneously. So you can expect the graph for current instead of this red variation. Let's say if we have yellow, so you can expect the graph for the current or the change in the current like this if you see it with respect to time. So you can consider any two instants. For instance, let's say you consider this point and this point with respect to this as any one of the instants. So the same current when you compare the two instants. So that means if you compare with respect to 0, so for an inductor, it's a very, very important point. So IL for inductor at 0 minus equals to IL for inductor at 0 plus. So if you remember, for a capacitor it was true for voltage. Now we're talking about an inductor. And the third important point about the inductor is an ideal inductor does not dissipate any energy. Same true for the capacitor. So series connected inductors, in order to combine the inductors connected in series, the total inductance, which is L equivalent, we're assigning it as, is given by the sum of the inductances L1 plus L2 plus L3. In order to look into the details of the derivation, please look at the course notes posted on D2L. Parallel connected inductors. So the equivalent inductance for parallel equivalent and parallel connected inductors is, so it's inverse of the sum of the inverses, so 1 over L equivalent, apologies, 1 over L equivalent is 1 over L1 plus 1 over L2 plus an inverse of L3, and it's true for any number of inductors, it's not limited to 3 only. We're looking at the response of first order RL circuit. So you have RL connected in series from a voltage source E. Here we're looking for the response of IL as a function of T. So you're expected to use all basic laws, including Ohm's law, KVL, KCL, at all possible loops and at all possible nodes, or for the components as well. And use the solution to differential equation. So here I'm just writing the final solution. So the solution for IL as a function of T is E over R plus, there is another term which is IL at T equals to 0 minus E over R, and then here e to the power negative T minus T0 divided by L over R. In order to have the details of this derivation, please look into the lecture notes posted. Okay, further analysis about the behavior of the inductor based on this equation. So if you look at the graph of IL as a function of time on the x-axis, you will find that at t equals to 0, so IL t0, let's say, I'll say at 0 equals to, so e to the power 0 comes as 1, so that's a e over r as 1, and it's going to lead to IL at 0 plus. Similarly, for t tends to infinity, so this is any minimum value. For t tends to infinity, IL, let's say we change its value to IL at a time t equals to infinity equals to, now we're putting here t equals to infinity, so that's going to leave u a 0, and the whole term goes to 0, so you're only left with e over r, which is one of the maximum possible values of IL. Now if you go back to the series circuit of R and C, you might realize that the current flowing through that series circuit of R and C is only E by R if inductor is replaced by a short. So this situation of t tends to infinity brings or changes this circuit, which you have RL connected in series, into something different. So what is that difference? So this was E, that was R. We're saying the current flowing through this circuit I is given by E divided by R. That's possible only when the inductor in this circuit is offering 0 resistance, and that's the case when it's short. So that means the inductor here at t tends to infinity, at t equals to infinity, is fully charged and can be replaced by a short circuit. So at time t equals to infinity, circuit will simplify into this. So I at t equals to infinity given by the value e over r. So going back to the graph, so here the first situation at t equals to 0 is here, any minimum current, and you can assume it as 0. Anytime t infinity, so you can consider any time t in here, and its value is e over r. So on the way you can see that it's an exponential variation, so this is how the graph will look like for the current, and this value is e by r. All over here saying t tends to infinity, but we can approximately the same system as we have for the capacitor. Depends on this time constant, so L over R in this case is defined as time constant, L over R is tau. In case of RC circuit, it's R multiplied by C. So now it's L divided by R. Tau. So approximately at 5 times tau, we consider that whatever state the inductor reaches into is fully, either it's fully discharged or fully charged. So 5 times tau is the time it takes. So the generic equation, again, I'm going to write for this. The generic equation will be y as the function of t equals to y at infinity plus y at 0 plus minus y at infinity e to the power negative t over tau. Okay, so this will be the equation which we will use to solve first order RL circuit. Again, I have a 7-step algorithm. These approximately on the same lines as we have used for the RC circuits. So we're going to discuss an example now, and we will use that 7-step algorithm. And in my lecture notes, that's on page 6 of the notes for inductors. It's week 9, page 6. So please refer to that. The circuit under consideration is the following, and the first part to pay attention is about the position of the switch. So it says that the switch is opening at time t equals to 0. Okay, so that means before time t equals to 0, the switch was in closed position at 0 time, and after 0, the switch is in open position. So the first step we use to solve the question is draw the circuit with the initial position of the switch. So redraw the circuit, draw the circuit with the switch in closed position. Let's do that. Okay, so the switch is in closed position and we have redrawn the circuit, so all other components are remaining same, and the values are also same. So 2 ohms, 4 ohms, 12, 16, and here we have an inductor. Okay, you can see that inductor is in a circuit where it's connected from the source, so inductor will be charging. And the second step is assuming that this circuit is in place for a long enough time for the inductor to be in its fully charged or fully discharged state, and in this case it will be fully charged. So the fully charged inductor will be replaced by a short. So we will erase the inductor and we will say it's replaced by a short in here, and we're expected to calculate the current flowing. So let's say this is the current flowing through this branch, so that current is considered as IL0 minus. So let's calculate that current. You can use any methods, current division, voltage division, Ohm's law, KVL and KCL. So calculate IL0 minus. Okay, so let's look at a bit of analysis in here. So what we have is this is a short circuit at 16 ohms is in parallel to the short circuit in a pure parallel combination. So current flowing through the 16 ohms in comparison to the short is going to be 0. So here you have 0 amperes of current flowing. So that makes whatever the current flows through 4 ohms is the one which is flowing through the short now. So the 4 ohms current is the same current as it flows through IL0 minus. So now that makes 4 and 12 in a pure parallel combination, and then you have 2 in here in series with that. So somehow through circuit reduction, if we can calculate this current in here, you can call it anything, let's say I, and then that I you can use current division at this node between 4 and 12. So using a circuit reduction, let's calculate this I. So I will be calculated as 40 divided by the total resistance. The total resistance in this case is 12 and 4 in parallel and then in series with the 2. So the total resistance goes to 5 ohms, and that gives you 8 amperes of current as I. So that's calculated now, and now you can apply current division here. So IL0 minus will be I'm using only two registers expression, so the other branch resistance 12 divided by 12 plus 416 multiplied by the current 8 amperes, so that gives you 6 amperes of current. So that is the second step in order to calculate IL 0 minus. The third step in this algorithm is IL 0 plus equals to IL 0 minus equals to 6 amperes. The next step, which is step number 4, is to draw the circuit with the final position of the switch, and the final position of the switch is the open switch. So let's draw the circuit and let's see what is the situation of the inductor is in terms of charge on. Okay, so that's the circuit with the final position of the switch as open. So now you can see that the inductor is not connected from the source, so this part of the circuit you can take out, and this is the final part which we are concentrating on. So what is happening to the inductor, whatever charge it has stored on in its magnetic field, that's discharging now because there's no source in the circuit where the inductor is connected. So the final position of the inductor in this case, that it will be fully discharged. So ideally what will happen is since current is what the inductor builds into, so there will not be any flow of current through the inductor. When we're saying, if we say, okay, we're labeling the situation for IL at time t equals to infinity, meaning this inductor or this circuit remains in this state for long enough time. So fifth step in this algorithm is to know IL infinity, and in this case it is 0. It might not be the case for all circuits. So that's completion of step number 5, and then the next step, step 6, is to calculate the value of the time constant tau. So time constant tau is calculated as L over the total resistance R equivalent. L is given to us as 2 henries, so in order to calculate the R equivalent, we'll be using the circuit with the final position of the switch. And again, in order to calculate R equivalent, all power sources will be turned off. So here in this circuit, it's the same circuit after t greater than 0. So this source, voltage source, will be powered off, and here that will be the points where we are trying to look at the circuit. Although in this case it's not much of the significance that you turn the voltage source off or not, because there is no connection of the voltage source to the circuit which contains the inductor. So here is the circuit. I have turned the voltage source off, and these are the points where you have to look in order to calculate R equivalent, and you can see this is where we are starting. So you have 16 and 4, and after 4, whatever current flows through, or whatever the path for 4 is the same path for the 12, because there's nothing going this way. So 12 and 4 are in series, that's in parallel to 16. That's the total resistance we have. So R equivalent equals to 12 plus 4, and that's going to be in parallel to 16. So it's actually 16 in parallel to 16, which gives you 8 ohms. So tau is L over R. L is 2 henries, and resistance is 8 ohms. That gives you 1/4, and tau is the time, so the units are seconds, as we have inductor in standard unit of henries and resistance in standard units of ohms. So that was the step number 6. The step number 7 is to put the values in the final equation. So the final equation was ILT equals to IL infinity plus IL 0 plus minus IL infinity and e to the power negative t over tau. So I'm writing IL t equals to IL at infinity was 0 plus and this value was calculated as 6 amperes minus this value was 0, e to the power negative t, and we calculated tau just on the previous test, step 1 by 4. So I'll put that 1 by 4 here. Further simplification, so 0 goes off, it's a 6 e to the power negative 4t, and this equation is true for t greater than equals to 0, and it's also the units of this expression. Don't forget to write that. The units here are amperes because it's about the current. Okay, so that's the solution. Thank you.